Hello everyone. The title of this video is Use the Product Property to Simplify Radical Expressions, or roots, right? Radical expressions and roots are the same thing. All right, so every exercise I'm going to do in this video is taken directly from a free online textbook at openstacks.org, and it is their Intermediate Algebra 2nd edition text. I am in section 8.2 titled Simplify Radical Expressions. And in this video, I will be working on exercises 55 all the way to 86. So that's 32 problems, right, and all their parts. Each problem, right, each of these 32, I'm going to call example 1 for number 55. I'll call number 56 example 2 in the video, example 3 for number 57, etc., right, all the way down to example 32 will be exercise 86. I will have timestamps for each of these exercises, each of these examples in the description of the video below. So if you'd like to see a particular problem, just go to that example's timestamp, right? You're going to have to count how many examples that is, but that shouldn't be too hard. And then go to that timestamp. One request I also have is that when I bring up a new example, a new exercise, pause the video and try to work on it yourself first before watching me do it. Because if you're just watching me do it and not practicing yourself, you're probably not learning much of anything. Alright, so in these exercises we're asked to use the product property, which I'll write out for you and explain, to simplify radical expressions. Alright, so I have these written out. Again, example 1 is exercise 55 in this section. But before I get into all these, let me take it to a new page and write out what this product property is. So like I said, every example we're asked to use the product property to simplify the radical expression. I'll talk about what that means. And later on, and I'll just bring it up right now, we should be using absolute value signs as needed. I hope you've been watching my videos in other sections, but you saw in section 8.1 of this text that whenever you took an even root, square root, fourth root, sixth root, etc., when you took an even root, right, that even root symbol was asking you for the positive even root. So at the end, you should be using the absolute value symbols when you're taking even roots. When you're taking odd roots, cube roots, fifth roots, seventh roots, etc., you don't need absolute value symbols. Right? Odd roots can be positive or negative. Alright, so let me talk about this product property for radicals or roots. So that is, if I have and this is for any root, okay, take the nth root of a product. So in the radicand here, underneath the symbol, we have a product, say A times B, right, a product, multiplication in here. You can split this up. Say that the nth root of A times B is equivalent to the nth root of A multiplied by, right, times the nth root of B. Right. Now, this property only holds if the nth root of A and the nth root of B are real numbers. Right. So this is only working if the nth root of A and the nth root of b are real numbers. Okay, and you saw, again, hopefully you've been watching, paying attention, reading the text. You saw in section 8.1 that if you took an even root, right, if you had an even index, square root, fourth root, sixth root, etc., the radicand couldn't be a negative number in order for the expression to be a real number. Right, so remember that the square root of -2 or the fourth root of -1 or the sixth root of -18, whatever, these are not real, right? Not real numbers. So in other words, if n is an even number, then a and b need to be positive, right? Because if either one of these factors is a negative number, one of these won't be real, and the property will not hold. All right, so this property only holds for real numbers. Okay, please understand that. Okay, so how we're going to use this to simplify a radical is to break our radicand up into something that can be written to the nth power times something that can't be written to the nth power. All right. So you'll see hopefully what I mean after all these bunches of examples that I'm going to go through in the video. All right. Okay. So here we're asked, example 1, I'm asked to simplify the square root of 27. So notice it is a square root. So what I'm trying to do when I'm going to use this product property, I'm going to rewrite this radicand. Well, first I'm going to factor the radicand completely. Let me say it that way. All right. So first, I'm going to take 27 or whatever number, whatever expression is inside the radical symbol. I'm going to factor it completely. So 27, when you break that down completely, is 3 to the third power. All right, 3 to the third power. Now, if this was the square root of a square, right, 3 to the second power, that would be wonderful, right? But that's not a square. So now what I'm going to do is I'm going to split up the factors using the product property. All right, so here comes the product property use. I'm going to take this 3 cubed, square root of 3 cubed, and break it up to a square root times a square root. And then inside the 1 square root, I'm going to put a square. Right, because it is a square root, right? And we'll see later, we'll get to cube roots later. When I do this with cube roots, in one of the radicals, I'll want a cube. And if I do it with fourth roots, I'll want a fourth power. So remember, a square is just any expression that can be written to the second power. All right, pay attention to your index. So 3 cubed, I can break that up to 3 squared times 3 to the first. So you see I break up 3 cubed, right? 3 cubed is just 3 squared times 3, isn't it? Right? And 3 squared is a square, right? It is something to the second power. So in one of the radicals, I want to put something that can be written to the second power, a square, for these square roots. And then in the other square root, I want to put a non-square, something that can't be raised, can't be expressed to the second power. All right, so over in this radical I have a non-square. All right, now the other rule I want to bring up, the other rules that we're going to use here, and this should be a recap. So hopefully you recall from an earlier video or last section that if n is even, so square root, fourth root, sixth root, and so on, the nth root of an nth power, right, the nth root of something to the nth power, was the absolute value of that x, right? Absolute value of the base. And the reason that absolute value symbols were used is because, when this is an even root symbol, they're asking you for the positive one, the not negative root. Also, we're going to run into odd roots throughout this video as well. If n is odd, cube root, fifth root, seventh root, and so on. If you take the nth root of an nth power, they just undo each other. You're left with the base, right? And you don't need absolute value symbols, right? Because an odd root can be positive, an odd root can be negative. All right, so hopefully you recall this from before. All right. And I'm gonna keep relying on this, using the product property to break it up into the nth root of an nth power times the nth root of a non-nth power. Right, just like I have here, square root of a square times the square root of a non-square. And it's the square root of a square, the nth root of the nth power, that we will simplify. Now the square root of 3 squared would be the absolute value of 3, but 3 is already positive, so I don't need the absolute values. Right? So just 3. Square root of 3 squared is 3, and then times the square root of 3. Right? The square root of the non-power, the non-square, I can't do anything with. Can't simplify that any further. And here we go. This is what we're being asked to do. I'm trying to rewrite the expression so that the radicand doesn't have any more perfect powers in it as a factor. And if it's a square root, I want the radicand to not have any more perfect squares as factors, which 3 is not a perfect square, and 3 cannot be factored into something with a perfect square. So the square root of 27 is equal to 3 times the square root of 3. Now, if you'd like to check this out, I'll put check. Use a calculator. Right, especially when there's just numbers involved. Now, if there are variables, you just plug in numbers to the variables and check with the calculator. But let me bring up a calculator. Right. So, like I said, the square. Let me punch both these in. I'll punch in the original expression we had, which was the square root of 27, and you're going to see that that's 5 point something. And then I'm going to enter the expression I got at the end and see if they're exactly the same value. And they should be if I'm doing things correctly. So I'm going to enter 3 times the square root of 3. And look at that. 5.196152423. It is the same value. Right? So these are equivalent. The square root of 27 and 3 times the square root of 3. Right? And I'm going to be doing this for a lot of these. Right? Alright, so number 2. Same thing. Alright, same thing. It's another square root. So when I use the product property later, I'll break it up to a square root times a square root. And in one of the square roots, I'm going to have something that can be written to the second power, right? So basically anything with even powers. And then in the other square root, I'll have the factors that can't be written to the second power. All right, so the square root of 80. Now 80, when you factor 80 completely, 80 is 16 times 5, or 2 to the 4th times 5. Right, there's 80 factored completely. And you could do the factor tree stuff. I'll leave it to you. And then I look through here and think, all right, when I break this up, using the product rule, I'll have the square root of something that can be raised to the second power times the square root of something that can't be raised to the second power. Any even powers, anything with powers 2 or greater, I can pull out something that's a perfect square. Like 2 to the 4th is a perfect square. And I'll show you why in a second. 2 to the 4th can be written as an expression to the second power. And the only thing in here, the only factors that can't be expressed as something to the second power is the 5. So I put 5 in the other square root. Again, this is using the product property. All right, once again, this first one, I'm going to write it as a square. 2 to the 4th, that's 2 to the 2nd squared, right? Power to a power rule. So here's my square root of a square. So the result should be the absolute value of 2 squared. Well, that's just 4, right? Times the square root of 5. And then that square root with the non-squares in it, just stays the way it is because you can't really simplify that any further. So this is 4, right? 2 squared times the square root of 5. And there you go. The expression I started with, and this should be should have the same value. Let's test that. All right, so again, I'm going to pull up a calculator, and we will test those values. So first was the square root of 80, which is 8.944279191 right? And the final expression we got was 4 times the square root of 5. So let's check that. 4 times the square root of 5, and indeed it is the same number. And it's also considered simplified because 5 doesn't have any perfect squares that are factors of it, other than 1. Okay, moving on. So yeah, this is really all I'm doing. The whole video, every example. Later on we'll see some expressions with variables, some letters. We'll also see different roots, but I'm still basically doing the same thing every single time. Alright, so the square root of 125. Now if you were to factor 125 completely, that would be 5 to the 3rd power. 5 times 5 times 5. And once again, that's not a perfect square, but 5 to the 2nd is, right? And you can think of this just like 3 to the 3rd. You can think of this as 5 squared, a perfect square, times 5 to the 1st. And so that's how I'll break it up, right? The square root of 5 squared times the square root of 5 to the 1st, right? That'll be the square root of 5 cubed. And now I have what I want, the square root of a square times the square root of something that is not a square. Right? And the square root of 5 squared would be the absolute value of 5, but that's just 5, right? Because it's already positive. So I have 5 times the square root of 5, and again, they usually just write it next to each other like I've been doing. Right? 5 root 5, you might hear someone say. 5 times the square root of 5. Again, let's check it out. All right, like I said, I'll do this for a bunch of these, right? And you should be as well. All right, so let's take the square root of 125. Get 11 something, right? 11.18, blah blah blah. And then we said that was equal to 5 times the square root of 5. Right? 5 times the square root of 5, and you see indeed that is the same number, same value. Wonderful. All right, let's keep going. The square root of 96. Now this is the square root. This is 32 times 3. 32 is 2 to the 5th power times 3. That's 96. And again, now these don't have even powers, but there are even powers hidden in here, right? Think about it. 2 to the 5th is 2 to the 4th. And any even power can be written as a square, right? We're square root here. So I'm trying to think of how to write this as the square root of squares times the square root of not squares. So 2 to the 5th, right? That's 2 to the 4th times 2 to the 1st. That's 2 to the 5th, right? And then you got 3 to the 1st, so that's not a square, right? 3 to the 1st, and you can't pull any squares. If that was 3 to the 3rd or 3 to the 5th or whatever, you could pull some even powers out, but it's just 3 to the 1st, so that's going to go in the non-square category. And then again, I'm going to write this as a square, right? I want the square root of a square. So remember, this is 2 to the 4th. That's 2 squared squared, or 4 squared, right? Just like earlier, I had 2 squared squared. That's 4 squared. 16, same thing. So now I have the square root of a square times the square root of a not, the rest of it's not squares, something that can't be written to the second power. 2 times 3 is 6, right? And so now the square root of 4 squared is, right, it's the absolute value of 4, but that's just 4, times the square root of 6. All right, and this is as simple as it gets, once again, because 6 doesn't have any perfect square factors, right, other than 1, just 2 and 3. All right, once again, I'll bring up a calculator. Let's test this out. So I started off with the square root of 96, 9.79795, and I said this is equivalent to 4 times the square root of 6 here, right? So 4 times the square root of 6, indeed the same value. Fantastic. Okay. Alright, so I'm going to stop doing the calculator check for the next few examples, because these are all square roots. I'll come back to the calculator check when we get to some cube roots or fourth roots, some other roots. Alright, so some more examples. Example 5. The square root of 147. Now 147 is 3 times 49. So that's 3 times 7 squared when you factor it completely. And then looking at all these factors, right, we have a square root. So once again, I want to break it up, using the product property, to the square root of some square, something that can be raised to the second power, times non-squares, square root of non-squares. Well, there's a perfect square right there, 7 squared. And then the only other factor left is 3. Right? That'll go in this square root with the non-squares. And the square root of 7 squared would be the absolute value of 7, but that's just 7, right? Times the square root of 3. Alright, and again, you can test this with a calculator. The square root of 147 should be the same value as 7 times the square root of 3. Wonderful. Okay, so here, so once again, I'm going to square root of 450. 450, this is 45 times 10, that's 9 times 5, that's 3 times 3 times 2 times 5. So 2 3s, 2 5s, and a 2. And this is 2 times 3 squared times 5 squared. Alright, So I've factored 450 completely. And let's break it up using the product property. Right? The square root times the square root. In here I'm putting all the perfect square factors, right? All the factors that can be written as something to the second power. Well, there's already a 3 to the second power times, and there's also a 5 to the second power. So I'll put those in here. And the only factor left then is 2. I'll put that in this other square root with the non-squares. Alright, then you could even go further and use the product property some more. Say the square root of 3 squared is 3, the square root of 5 squared is 5. So I have 3 times 5 times the square root of 2, but 3 times 5 is 15. So we have 15 times the square root of 2. And once again, use a calculator to test this. Punch in the square root of 450, then punch in 15 times the square root of 2, and you should get the same value. Okay, 800. Let's break that up. Now 800 is obviously 8 times 100. This is 2 to the third. Right? 8's 2 to the third. 100 is 4 times 25, 2 squared times 5 squared. So 2 to the third, 2 squared, that's 2 to the fifth. Right. So 800, when you break it down completely, is 2 to the fifth power, and then you have 5 squared times 5 squared. Right. 32 times 25 would be 800. Alright, and once again, break this up using the product rule. Right. Product properties, square root times square root. In the first square root, right, I'm going to put all the factors that are, basically have even powers, that can be raised to the second. 2 to the fifth, that's an odd power, but the highest even power under that would be 2 to the fourth. So I can rewrite 2 to the fifth as 2 to the fourth times 2 to the first, and that 2 to the first is going to go under the square root without the perfect squares. And then 5 squared is an even power, so that'll go under the square root with the squares. All right, now we have seen the square root of 2 to the fourth already. That's 2 squared squared. All right, this is the same as 4 squared. The square root of 4 squared, which would be 4 times, using the product rule with this, the square root of 5 squared would be 5, then times the square root of 2. And 4 times 5 is 20, right? So this is 20 times the square root of 2. And there you go. Once again, use a calculator if you want to check it. Take the square root of 800, punch that in, then punch in 20 times the square root of 2, and you should get the same value. Okay. Now 675, right, example 8. This is 25 times 27, I believe. So yeah, 25, that'd be 25 times 25 times 24 would be 600, and then you have 3 more for the 75. Yeah, 25 times 27, and that's 5 squared, that's 3 cubed. So 675 breaks down completely to 3 cubed times 5 squared, 27 times 25. And then once again, I'm going to use the product property. Break it up to a square root times a square root. In this first root, I'm going to put all the perfect squares. Well, 3 cubed isn't a square, right? It doesn't have an even power. But, the next highest even number under that would be 3 squared. So I can break that up to 3 squared times 3 to the first, right? And 3 to the first would go in the other square root with the non-squares. And then all that would be left is, 5 squared. So that goes under here, with the perfect squares. Then you can use the product property again. Square root of 3 squared is 3 times the square root of 5 squared is 5. and you have times the square root of 3. And 3 times 5 is 15, so this is 15 times the square root of 3. And once again, double check. Punch in the square root of 675, punch in 15 times the square root of 3, and you should get the same result. Alright, so now all these first 8 examples were square roots, right? Square roots. So when I broke it up using the product property, right, I was taking the square root of squares times the square root of non-squares. But that changes when you have different roots, right? Roots other than square roots. So my next examples are all like this, and this is where I'll start going back to the calculator to do some checking, at least just for this page. Alright, so number 9, part A. See, pay attention. Now we have a fourth root. The fourth root of 32. And we're asked to simplify it, right? Basically factor out any fourth powers that go into 32 evenly. So just like the square roots, this is equal to the fourth root of, and then 32, I'm going to factor 32 completely. That's 2 to the 5th power. Alright. And then I'll use the product property. Alright, so I factor the radicand completely. And I'm going to use the product property to write this as a fourth root times another fourth root. Alright, but this time, instead of squares in this first radical, I want fourth powers, right? This is a fourth root. I want fourth powers, things to the fourth power, or things that can be written to the fourth power. So basically anything with a power that's a multiple of 4. So anything with a power of 4 or 8 or 12 or 16, that's what I want inside this first root. And then in the next root, I want not fourth powers, right? Things that can't be written to the fourth power. Right? Non-fourth powers or not fourth powers. Right. Well, 2 to the 5th, 5 is not a multiple of 4. So then you got to think, what's the largest multiple of 4 less than 5? Well, that would just be 4. So I could break 2 to the 5th up to 2 to the 4th times 2 to the 1st. Right? 2 to the 4th times 2 to the 1st is 2 to the 5th. So the fourth root of 32 is equal to the fourth root of 2 to the 4th times the fourth root of 2. And now I have something in here that I want. Right? I have the fourth root of a fourth power, so those will undo each other, and I'm left with the absolute value of 2. But, the absolute value of 2 is just 2. So this is 2 times the fourth root of 2. All right, and this expression should be equivalent to the fourth root of 32. Alright, so once again I'll pull up a calculator and we'll check that. So I'm doing the fourth root symbol now. All right, 4 in the index. Fourth root of 32 is what I started with. And you see that's 2.37 something. And we said just now that that was equivalent to 2 times the fourth root of 2, right, with the smaller radicand. So 2 times the fourth root of 2. And indeed, they are the same number. So, did a good job there. Alright. So next one. Pay attention. 9 part B. Remember, there I was looking for fourth powers. Powers that were multiples of 4. Here, I'm looking for fifth powers, right? Powers that are multiples of 5, 10, 15, 20, and so on. So it's the fifth root of 64. So just like all the others, the first thing I'm doing is factoring the radicand completely. Now 64 is just 2 to the 6th. And when I split this up with the product property, right, I'll have a fifth root times another fifth root. And this time, what I want to put in this first radical are fifth powers, right? Powers that are multiples of 5. As I said, 5, 10 to the fifth power to the 10th power. Anything that can be written as something to the fifth. So here I want fifth powers, and over here I want, not fifth powers. So 2 to the 6. Now 6 is not a multiple of 5. So then you got to think, what's the largest multiple of 5 less than 6? That's 5. So I can break this up to 2 to the 5th. All right, there's a fifth power times 2 to the 1st, right? 2 to the 5th times 2 to the 1st, that's 2 to the 6th. So this fifth root of 64 is equivalent to the fifth root of 2 to the 5th times the fifth root of 2. And this is the fifth root of a fifth power, so those all undo each other. I'm left with just 2, right? Not the absolute value of 2, right? This is an odd root, but it's still 2 either way, times the fifth root of 2. The fifth root of 2. And there we go. And again, let's test this out. Let me enter these into my calculator and see if we get the same value, and we should. Right. So the first value I was given was the fifth root. Right, so I put the 5 in the index there. The fifth root of 64. Right, it says 2.29 blah blah blah. Right. And we said this was equivalent to 2 times the fifth root of 2. 2 times the fifth root 2. And it is indeed the same number. Fantastic. Alright. But yeah, so you really got to pay attention to the index, what root is being taken. Because then you'll be looking, when you break it up with the product property, you're going to look for powers that are multiples of that index, right? Powers that are multiples of 5 or multiples of 4. Here it's 10 part A. I have a cube root. So I'm looking for powers that are multiples of 3 now. I'm looking for cubes, third powers to use. Alright, so the first thing I do, as with every example, we're taking the cube root of, and then 625 is 25 times 25, so 5 to the 4th. 5 to the 4th power would be 625. And then after factoring the radicand completely, then I'm going to split it up here using the product property. So I'll have a cube root times another cube root. And this time, inside this radical, I want cubes. Things that can be written to the third power, right? So I'm looking for powers that are multiples of 3. 3, 6, 9, 12, and so on. And then in this radical, I'm going to put, not cubes, right? Just not. So 5 to the 4th. Now 4 is not a multiple of 3, right? But the largest multiple of 3 less than 4 is 3. So I could split up 5 to the 4th as 5 cubed times 5, right? And put one of them in the cube radical and the other one in the not cube radical. Alright, and then the cube root of 5 cubed is just simply 5, right? Cube and the cube root undo each other, and then I have 5 times the cube root of 5. And there we go. And once again, right, again, just for this page, I'll test it with a calculator. So we were given the cube root of 625 to start. 8 point something, and we said at the end there that it's equal to 5 times the cube root of 5, and look, they are the same number. Fantastic. Alright, And then here in part B of number 10, got a sixth root, right? So now I'm looking for sixth powers that are multiples of 6 to put in the one radical. So 6, 12, 18, 24, etc. All right, so first, as usual, as with all these, I'm going to factor the radicand completely. Now 128 is 2 to the 7th. Right, we saw earlier that 2 to the 6th was 64, right up here. And this is just double that, so this is 2 to the 7th. All right, and then I'm going to break it up, right, using the product property to a sixth root times a sixth root. And in this radical, I'm looking to put sixth powers, right? Something that can be raised to the sixth. And then here I'm putting, not sixth powers. Now this factor here, 2 to the 7th, 7 is not a multiple of 6. But, I can break this up. The highest multiple of 6 less than 7 is 6. I can break this up to 2 to the 6th times 2 to the 1st. All right, that's 2 to the 7th. So we have the sixth root of 2 to the 6th times the sixth root of 2. And the sixth root of 2 to the 6th would be the absolute value of 2, right? Even root, but you don't need the absolute value here because 2 is already positive, so it's just 2 times the sixth root of 2. All right, and then one more time here, for a little while anyway. I might do it later when we're checking other values. We'll bring the calculator back, right? And we were given sixth root this time, right? So sixth root of 128 to start. And so this is 2 point something. And we said that that was equal to 2 times the sixth root of 2. And indeed they are the same number. Fantastic, right? Great job. Alright, yeah, and again I'm doing the same thing every time. I'm factoring the radicand completely, then pay attention to your root, right, and then breaking it up using the product property to one root has perfect powers in it, the other one doesn't, and then simplify. Right. So very similar problems here. Right. Again, you just got to pay attention to the root. 11 part A. We're taking the fourth root of 64. Now we've already seen 64 broken down completely. All right, so this is the fourth root of 2 to the 6th. And then I break up, to using the product property. Fourth root times the fourth root. And inside this I want a fourth power, right? Something with a power that's a multiple of 4, 4, 8, 12, and so on. And then over here, things with powers that aren't multiples of 4. Powers that are less than 4 in this other one. So 2 to the 6th. Now, 6 is not a multiple of 4, but there is a multiple of 4 less than that, and that'd be 2 to the 4th, right? 4. So I can pull 2 to the 4th away. Right? We can write 2 to the 6th as 2 to the 4th times 2 to the 2nd. Right? There'd still be 2 factors of 2 left over in here. Right, so again, you see over here, multiples of 4 are the powers. Here, all the powers are less than 4. And now I have what I want. The fourth root of 2 to the 4th would just be the absolute value of 2, or just 2, times the fourth root of, now 2 squared we can simplify to 4. Right? Once you've split them up, you can write what the numbers are after. And again, I leave it to you to test this in a calculator. Take the fourth root of 64, and then punch in 2 times the fourth root of 4, and see that you get the same result, and you should. Okay, next we have the cube root of 256. So this is the cube root. Now 256 is 2 to the 8th. It's another nice power of 2. 2 times 2, 8 times. 2 to the 8th power. Alright, so again, I'm going to break this up using the product rule. Right, to a cube root times a cube root. In this cube root, I want all the powers to be a multiple of 3. I want cubes. So 3, 6, 9, etc. And in this radical, I want all the powers to be less than 3, right? Non-cubes. Now 2 to the 8th, 8's not a multiple of 3, so it's not a nice cube right now. But there is a multiple of 3 that's less than 8, and that would be the next highest one would be 6. So I can break up 2 to the 8th to 2 to the 6th times 2 squared. Right, so again, you're seeing in here, the powers are all multiples of 3, perfect cubes. And in here, the powers are all less than 3, so not perfect cubes. Now, if you want to keep rewriting this, actually write it as a cube. Right? This is the cube root of 2 to the 6th. Right? That's 2 squared to the 3rd. Right? Power to a power rule. There's your cube. Times, and then you have the cube root of, and then 2 squared is just 4. And so now I have a cube root of a cube. Right? Those will undo each other. I'm left with just 2 squared, or 4. So I have 4 on the outside. 4 is the value of this first radical. Times, and then the cube root of 4. And there you go. And again, I leave it to you to check with a calculator. Enter the cube root of 256. Then enter 4 times the cube root of 4. And you should get the same value for both. Okay. Next, we have the 4th root now. Right, so again, when I break it up, one radical is going to have all powers that are multiples of 4, right? 4th powers, 4, 8, 12, 16. The other radical is going to have powers less than 4, not 4th powers. Right? All right, so first, let me break up 3,125 here. Now, do a little factor tree. Now that would be 125 times 24, 20, times 25. Okay, so 5 cubed, 5 squared. This is 5 to the 5th. So I'm doing the 4th root of 5 to the 5th. All right, that's 3,125. And then once again, after factoring the radicand completely, I'm going to use the product property to break it up to a 4th root times another 4th root. And in this first one, I want all the powers to be multiples of 4. I want 4th powers. In the second one, I want all the powers to be less than 4, right? Non-4th powers. 5 to the 5th can be broken up to 5 to the 4th times 5 to the 1st. Right, that's 5 to the 5th. And there's your 4th powers, not 4th powers. Right? And now I have the 4th root of a 4th power. Those will undo each other. I'm left with just, the absolute value of 5, or just 5 here, times the 4th root of 5. All right, and I leave it to you to check. Punch this in a calculator at the 4th root of 3,125. Also try punching in, 5 times the 4th root of 5, and they should give you the same number. And then part B, you have the cube root, right? So again, I'm looking for 3rd powers now, powers that are multiples of 3, 3, 6, 9, and so on. First step's always the same, right? Going to factor 81 completely. Now 81 is 3 to the 4th power. And then I'm going to break this up, right, using the product property to a cube root times a cube root. In this first radical, I'm going to have all the powers be multiples of 3. In the next one, I'm going to have all the powers be less than 3. Right? So cubes and not cubes. Oh, we can easily do that by, you can break up 3 to the 4th into 3 cubed times 3 to the 1st. So I have the cube root of 3 cubed times the cube root of 3. And the cube root of 3 cubed would just be 3. It's a cube root of a cube. So I have 3 times and then the cube root of 3. Alright, and test this with a calculator. Punch in the cube root of 81. Then punch in 3 times the cube root of 3, and you'll see that they both give you the same result. Okay. Now we're getting into the problems where there are variables. So you really have to, again, remember this rule here. I brought this up earlier in the video. Remember, if n is even, you should be using absolute value symbols. Right? The even root symbol means they're asking you for, that symbol asks for the not negative root. Okay, so the nth root of an nth power when n is even is the absolute value of the base. Odd power, you don't need to worry about it. Odd roots are fine. Odd root of an odd power, you're just left with the base itself. It can be positive or negative. But the even root, right, has to be not negative, right? So absolute values may be necessary. And so keep that in mind. All right, so exercise example 13 here. Now each of these is going to have 3 parts for a little while. All right, so part A, square root, right? Even root. And being that this is an even root, the result can't be negative. So I might need to use absolute value symbols. Alright, well, just like earlier, I'm going to break this up using the product rule to the square root times the square root. In here, I'll have a perfect square, right? Something to basically an even power. I want powers in here that are multiples of 2. And then this other radical, I want, not perfect squares, basically with powers less than 2. Right. Now y to the 11th. 11 is not a multiple of 2, so that's not a perfect square, but y to the 10th is. So I can break up y to the 11th to y to the 10th times y to the 1st. So this is the square root of y to the 10th times the square root of y. That's the square root of y to the 11th. And then this is a perfect square, right? Now, if you want, you can write this as the square root of a square, right, using that power to a power rule. Y to the 10th is, y to the 5th squared. So now I have the square root of a square times, the square root of y. Right, and remember, the square root of a square is the absolute value of the base. So this is the absolute value of y to the 5th times the square root of y. And there you go. This is totally fine here. Now remember, you could also pull out y to the 4th, because that'll never be negative, and throw it outside the absolute value symbols, but I'll just leave it this way for now. Because if you hopefully you remember that anything to an odd power can be negative. That's why we need the absolute value symbols around this, because the result of an even root can't be negative. Right? So anything to an odd power, I need absolute value symbols around to ensure that it stays not negative. But if you get something to an even power, right, if this was y to the 4th, y to the 6th, y to the 8th, you can still put the absolute value symbols. They're just not necessary. Right, because any number to an even power, any real number to an even power, is not going to be negative anyway. Right, so that kind of scenario may come up as we go through these. All right, now part B, doing a cube root, that is an odd root, so I don't have to even think about using absolute value symbols. They are not necessary. Odd roots can be positive or negative. All right, so once again, using the product rule here, I'm going to write this as a cube root times a cube root. And in this first radical, I want the powers that are multiples of 3. Right? I want cubes, perfect cubes. In the other radical, I want powers that are less than 3, right? Not perfect cubes. R to the 5th, that's not a perfect cube, but 3 is less than 5. That's a perfect cube. R cubed is a factor of R to the 5th, and I can break up R to the 5th to R cubed times R squared. And now I have a cube of a cube, so those undo each other. I'm left with just R. No absolute value. Okay, no absolute value. It's an odd root. R times the cube root of R squared. And there you go. That's as simple as that gets. Now, if you'd like to check these out, all right, if you'd like to test these out, just replace R with some values. You could have done this with A as well. All right, you could have done this with A as well. In fact, I will start with 13 part A. If you want to test these out, just replace Y with different numbers, or replace R with different numbers, and see that the expression in the beginning is exactly the same as the expression at the end. All right, so looking at number 13 part A again, sorry. Let's start with, I'll just replace Y with 3, right? So if I took, what's the square root of 3 to the 11th power inside the square root, right? That's just replacing Y with 3. And I get, 420 point whatever. Now let's go to the end here and replace Y with 3. Now, I don't need absolute values around this because 3 is positive already. But if you want absolute value, you can, right? I go here, math, and then num absolute value. Absolute value of, replace Y with 3 again, go 3 to the 5th. And then after the absolute value, times the square root of Y, the square root of 3. And this should give me the same result, and indeed it does. And you can replace Y with anything. Well, any non-negative number, right? Because this is an even root. Remember, if you replace Y with a negative number, the square root of a negative won't be real, and it'll come up with an error on the calculator. All right. And let's do one check of part B. And this will be the last calculator used for these variable ones. Right? But the original expression was the cube root of R to the 5th. So I'm just going to replace R with -2. Right? Really, whatever you want. Odd roots, you can replace the variable with whatever you want. Even roots, you got to pay more attention. So I'm doing the cube root of let's say -2 to the 5th power. All right, replacing R with -2. And you say I get -3.17 blah blah. Now let's look at the expression we got at the end. Right, this R times the cube root of R squared, and see if we get the same thing. Now R is -2, so -2 times the cube root of R squared. The cube root of -2 in parentheses squared. And indeed the same number. And you could do that with any value of R here. Right, and see that the value of the original expression is exactly the same as the value as what we got at the end. And that should always be the case when you say two expressions are equal. They should always be the same value no matter what you plug in for the variables, as long as what you plug in is allowed. Right? Okay. Alright, so yeah, that's the last I'm going to do with that. But I'll leave it to you to check with the calculator all these other ones. Alright, so we're back to an even root. Fourth root. And I'm going to break this up. We have the fourth root of s to the 10th. Break it up to a fourth root times a fourth root. Now, 10 is not a multiple of 4, but 8 is. So I can break up s to the 10th to s to the 8th. And I would need to multiply s to the 8th by s squared, right, to get s to the 10th. So this is the fourth root of s to the 8th times the fourth root of s to the 10th. S to the 8th is a fourth power. And let me show you how to write that, right? And that would be the fourth root of, now, s to the 8th is s squared to the fourth, right? Power to a power. So here I have the fourth root of a fourth power times, and then the fourth root of s squared. And this would be, the absolute value, because it's an even root. Absolute value of s squared. Right, the fourth root and fourth power undo each other. I got absolute value of s squared times the fourth root of s squared. Now you've seen me do this in previous videos. I hope you've been following, right? For this particular question, the absolute value symbols are not necessary because I have, s to an even power, right? Even power, absolute value not necessary. Because it'll, when I take a number and square it, a real number squared will never be negative anyway. So a simpler version of this would just be, the absolute value of s squared will just be s squared times, and sorry about the clutter here, the fourth root of s squared. All right, so this is a little tight here. I'm sorry about that. But it's s squared times the fourth root of s squared. And once again, if you want to test it out, replace s with some number and see if the original expression has the same value as the final one. All right. Number 14, part A. Now we're back to a square root, but it's still an even root. And what I'm going to do is break it up to a square root of a square times the square root of a not square. Now 13 is not a multiple of 2, but 12 is, right? So I can break this up to m to the 12th times m. And m to the 12th is m to the 6th squared, right? I've got a square root here, so I'd like to write this as a square. This is m to the 6th squared. Right now I have a square root of a square times the square root of m. And square root of a square, they undo each other. This is the absolute value of m to the 6th. Remember, even roots, you should be doing that. Absolute value times the square root of m. But wait a minute, just like in the earlier question, I don't need absolute value symbols around m to the 6th, right? Any real number to an even power is not going to be negative anyway. So the absolute value of m to the 6th is just m to the 6th. And then you have still times the square root of m. And there you go. And again, once again, test it out. Replace m with some values and see if these are actually the same expression, same value. They should be. Part B, got an odd root. Alright, so fifth root, I don't need to worry about absolute values at all. Don't need them. So I break this up to a fifth root times a fifth root. Now 7 is not a multiple of 5, but 5 is. You can break this up to u to the 5th times u squared. And then the fifth root of u to the 5th would just be u. So I have u times the fifth root of u squared. Great. And last on this page, part C, number 14, part C, got a sixth root. So again, it's an even root, so I should be using absolute values when necessary. So again, I break this up to a sixth root of a sixth power times a sixth root of a non-sixth power. Now 11, the power in here, v to the 11th. 11 is not a multiple of 6, but 6 is, right? So I can break this up to v to the 6th times v to the 5th. And here I have a 6th root of a 6th power. Right, the 6th root of v to the 6th would be the absolute value of v. And this time the absolute values are necessary because this is an odd power. Right, v to the first, that can be negative if v were a negative number, so I need to make sure it's not negative by taking the absolute value. Times the 6th root of v to the 5th. Right, so it's the absolute value of v multiplied by the 6th root of v to the 5th. Alright, and got a bunch more now that are very much like that. So number 15, very, very similar stuff. So I'm going to start speeding up a little bit. Square root of n to the 21st. Alright, I could write this as the square root of n to the 20th, right? That would be a perfect square, right? Even power. Times the square root of n, right? A not perfect square. And n to the 20th is n to the 10th squared. So this would be the absolute value of n to the 10th, but you don't need absolute values around that because it's an even power. It's always positive anyway. So it's n to the 10th times the square root of n. And again, double check, test it out. Replace n with some numbers that are not negative, right, because this is square root. And see if the value of the original expression is equal to this. Alright, part B, I got a cube root. I break it up to a cube root times a cube root. Now 8 is not a multiple of 3, but 6 is, right, the next highest one. That's a multiple of 3. So I can break this up to q to the 6th times q squared. And then q to the 6th, that's q squared cubed. Right. So I have the cube root of a cube, right, times the cube root of q squared. And the cube root of a cube, they undo each other. I'm left with just q squared. Right. Q squared times the cube root of q squared. Right. Great. And again, if you want, replace values of q and see if these are the same as the original. And there was no reason to think about absolute values there because it was an odd root. Okay. Part C, 8th root of n to the 10th. So it's an even root. It means I might have to use absolute value symbols, right, to make sure things stay not negative at the end, stay positive. Alright, so I break it up to an 8th root times an 8th root. N to the 10th, 10 is not a multiple of 8, but 8 is, right? So I can break that up to n to the 8th times n squared, right? That'd be n to the 10th. Here I have an 8th root of an 8th power, so that's the, just n, but the absolute value of n. Remember, the even roots, you should be using absolute value symbols when necessary. And it is necessary here, right? N to the first power, this can be negative and I don't want it to be. Right, this symbol means I want the positive 8th root or the principal 8th root. So I have the absolute value of n times the 8th root of n squared. And there you go. And once again, replace n with some numbers and see if the value of the original expression is the same as the value of the last one. They should be. 16, very, very similar. Part A, another square root. So I'm breaking this up into the square root of a square. Now r to the 25th, that'd be r to the 24th, right? That's a square. Something with an even power. Times r to the first. So I can break up square root of r to the 25th to the square root of r to the 24th times the square root of r. Now r to the 24th is r to the 12th to the second. So this is just r to the 12th. Right? The square root of r to the 24th is r to the 12th. And since it's an even root, normally you would put absolute values around this, but again, I don't need it here. Any real number to an even power won't be negative anyway. So I don't need the absolute values here. So we have r to the 12th times the square root of r. Part B, got a fifth root of p to the 8th, odd root, so no need to worry about absolute values. So I break this up into the a fifth root times a fifth root. And I want a fifth power in here. Now p to the 8th, 8's not a multiple of 5, but 5 is. So I can break that up to p to the 5th times p cubed. Right, that'd be p to the 8th. And fifth root of a fifth power, those undo each other. I'm left with just p times the fifth root of p cubed. And there's that totally simplified. Alright, then fourth root, even root. So I may have to use absolute value symbols if necessary, right? So I'll break this up to a fourth root times a fourth root. M to the 5th would break up to m to the 4th times m to the 1st. Here I have a fourth root of a fourth power. Those undo each other. I'm left with m, but that could be negative. So again, this should be the absolute value of m for the not negative fourth root, which the symbol asks for, times the fourth root of m. So the absolute value of m times the fourth root of m. Okay, great. I'm still doing this, right? But now we'll have to do some factoring. Alright, so 17 has 3 parts, sure, but now there's some numbers coming back, numbers and variables in the mix. So just like I was doing with numbers before, I'm going to factor these numbers, factor the radicand completely. So 17 part A, we got the square root of 125 r to the 13th. That'd be the square root of 5 to the 3rd times r to the 13th. Right. Then again, I break it up. I factor the radicand completely, break it up to a square root times a square root. And in this first square root, I'm putting perfect squares, things with powers that are multiples of 2. Now 5 cubed, I'd have to break up to 5 squared, right? There's your perfect square, times 5 to the 1st, and the 5 to the 1st would go under the other radical with the non-squares. And then r to the 13th, well, that's not a perfect square, but r to the 12th is, right? So r to the 12th here, and then times r to the 1st, right, would be r to the 13th. And then I take square roots. Now the square root of 5 squared would be, the absolute value of 5, which is just 5. No need for absolute values around that. The square root of r to the 12th, I'm just using the product rule again with these, square root of 5 squared times the square root of r to the 12th. Now r to the 12th is r to the 6th squared, so this would be r to the 6th. And you can put the absolute value symbols around it if you want, but again, it's an even power, so the absolute value symbols are unnecessary. So I have 5r to the 6th times the square root of 5r. And there's as simple as that radical is getting. Right, the radicand doesn't have any perfect square factors anymore, so it's considered simple. And once again, replace r with some positive number. It's got to be positive because I don't want to take square roots of negatives. That's not real. And see if the value of this expression I started with is the same as the value at the end. 5 times r squared times the square root of 5r. Okay, next, same thing. We have the cube root of 108 x to the 5th. So just like the others, breaking the radicand up first, factoring it. Now 108, that's 2 times 54. 54 is 2 times 27. So it's 2 squared times 3 cubed. Right, 4 times 27, yeah, that would be 108. And then you have times x to the 5th, right? And now that I've factored the radicand completely, I'm going to break it up using the product property, right, to a cube root of cubes times a cube root of not cubes. Well, 2 squared, there's no multiple of 3 less than 2, so 2 squared is going to go in the not cube area, the not cube radical. Now 3 cubed is a cube, and so that's going to go in the cube radical, 3 cubed. The x to the 5th needs to be split up. 5 is not a multiple of 3, but it's not less than 3 either. So if x to the 5th, I can break that up to x cubed, right? There's a cube, times x squared. Right, so there's, again, all the powers in here are multiples of 3, so I got my perfect cubes. All the powers in here are less than 3, so they're not perfect cubes. No factors that are perfect cubes. And then I don't have to worry about absolute values here. It's an odd root. So cube root of 3 cubed is just 3. Cube root of x cubed is just x. Then we have times the rest, times that other cube root. That's the cube root of the non-cubes. Right? The cube root of, now 2 squared is 4. You should be simplifying your numbers. 2 squared is 4, and then times x squared. And here we go. Alright, so the cube root of 108 x to the 5th is equivalent to 3 times x times the cube root of 4x squared. And once again, replace x with some numbers and go to a calculator and see if these expressions indeed have the same value. Okay. Part C, again. This time it's a 4th root. So I'm going to first do what I've been doing, factor the radicand completely. 48 is 16 times 3, so that's 2 to the 4th times 3. That's 48, and then times y to the 6th. Right? And then the product rule comes in, right? 4th root times the 4th root. In the one radical, I want 4th powers, powers that are multiples of 4. And in the other radical, I want not 4th powers, so powers that are less than 4. 3, 2, 1. 2 to the 4th is definitely a 4th power, so that's going to go in the first radical, 2 to the 4th times. And then 3 to the 1st, that's not a 4th power, and there's nothing I can pull out of that. So that's going in the other radical. Y to the 6th has to be broken up, because 6 is not a multiple of 4, but it's also not less than 4. So this can be broken up to y to the 4th, right? That's a 4th power, times y squared. So y squared in the other one. Alright, then we have, the 4th root of 2 to the 4th is just 2, which doesn't need absolute values around it, it's already positive. The 4th root of y to the 4th would be y, but that needs absolute value around it, right? To ensure we get the non-negative even root, non-negative 4th root. Because y can be negative, so I need absolute value symbols around that. You got to pay attention with even roots. Times the 4th root of 3y squared. And there you go. And once again, you can replace y with some numbers and see, with a calculator if these actually give you the same value back or not. And they should. So pretty similar for the next few examples. Next bunch of examples, actually. So example 18, number 18. Part A, got another square root, so I might need absolute values. First, I'm going to break up the radicand. Now, 80 is 16 times 5. Right, 16 times 5, 50 plus 30, yeah. So that's 2 to the 4th times 5. Right, 2 to the 4th times 5 is 80. Then you have times, s to the 15th. Right, then once again, breaking this up using the product property to a square root times a square root. Perfect squares in here, not perfect squares in there. Now 2 to the 4th, that's a perfect square, right? The power is even. 5 to the 1st is not, so let's go in the other radical. S to the 15th can be broken up to s to the 14th times s. Alright, so in one I have 2 to the 4th times s to the 14th, all even powers, right, all perfect squares. multiples of 2 powers, you know. And then all these have powers less than 2, powers of 1, 5 times s. Now the square root of 2 to the 4th. Now 2 to the 4th is 2 squared squared. So this would be 2 squared or 4. 2 squared or 4. And it doesn't need absolute value symbols around it. The square root of s to the 14th would be s to the 7th, and that needs absolute values around it because, you know, s to the an odd power could be negative, and I don't want it to be with these even roots. So 4 times the absolute value of s to the 7th, then times the rest, right? Times the square root of 5s. And you could pull s to the 6th outside of the absolute value symbol because s to the 6th will never be negative, but this is fine. Alright, same thing here. But this time it's a 5th root, so I don't need to worry about absolute values. It's odd, odd root. So this is the 5th root of, now 96 is 32 times 3, so 2 to the 5th times 3. 96, and then you have a to the 7th. Once again, breaking this up with the product property to a 5th root of 5th powers times a 5th root of not 5th powers. Well, 2 to the 5th is clearly a 5th power. 3 is not a 5th power. And then a to the 7th can be broken up to a to the 5th, a 5th power, times a squared, you know, with a power less than 5, not a 5th power. Then the 5th root of 2 to the 5th would be 2, the 5th root of a to the 5th would be a. No absolute values because it's odd root, right? Don't worry about that. So we have 2 times a, and then times the rest, right? Times that 5th root of the non-5th power, the 5th root of 3a squared. And there you go. That's as simple as that radical gets. Alright, then we have a 6th root. Alright, so once again, I'm going to factor the radicand first. Alright, so we have the 6th root. Now 128 is 2 to the 8th power. Because we saw earlier, you know. No, that's 2 to the 7th. Yeah, 2 to the 7th. I am sorry, 2 to the 7th power. Because 2 to the 6th power, we've seen a bunch, is 64. And this is just double that. So that's 2 to the 7th, my apologies. So 2 to the 7th and then times b to the 7th. Alright, and once again, using the product property to break this up into the 6th root of 6 powers times the 6th root of not 6 powers. Now 2 to the 7th can be broken up to 2 to the 6th, right, a 6th power, times 2 to the 1st, a not 6th power. And b to the 7th, the same thing. I can break that up to b to the 6th, 6th, that's a 6. b to the 6th times b to the 1st. Okay, now the 6th root of 2 to the 6th would just be 2, no need for absolute values on that. The 6th root of b to the 6th would be b, but I need the absolute value, right? The absolute value of b needs to be non-negative, right? This isn't the non-negative even root symbol. Then times the 6th root of 2b. Alright, so we have 2 times the absolute value of b times the 6th root of 2b. Wonderful. Alright, again, test it out, plug in different values of b, and see if the original expression has the same value as the final one, and it should. Alright, let's keep going. Example 19, very, very similar. Right? Numbers and variables involved. Alright, so we got the square root now of 242 times m to the 23rd. So once again, I'm going to break this up completely. Now 242, that's 2 times 121, and 121 is 11 squared. So that's 2 times 11 squared times m to the 23rd. And I break it up to the square root of squares times the square root of non-squares. 2 is not a square, so it goes in the non-square radical. 11 squared, very clearly a square. And then m to the 23rd, I can break up to m to the 22nd, which would be a perfect square, right? Something with an even power, times m to the first. The square root of 11 squared is just 11. No need for absolute values. The square root of m to the 22nd would be m to the 11th power, but that can be negative, so I do need absolute value symbols around that to ensure that it's not. So I have 11 times the absolute value of m to the 11th times the square root of 2m. Great. Alright, fourth root now, so still an even root, still might need absolute values at the end, right? Always think about that with even roots. So we have the fourth root. Now 405 is 5 times 81, and 81 is 3 to the fourth. So that's 3 to the fourth times 5, right? That's 405. Times m to the 10th. Then I'm breaking it up, product rule again, product property. We take a fourth root of fourth powers times the fourth root of non-fourth power factors. 3 to the fourth is clearly a fourth power. 5 to the first is not. M to the 10th would be broken up to m to the 8th, right? 8 is a multiple of 4, so that's a fourth power, times m squared, right? Which would not be a fourth power. Power less than 4. The fourth root of 3 to the fourth would just be 3, no need for absolute values on that. The fourth root of m to the 8th would be m squared, which also doesn't need absolute values, because any real number to an even power is not going to be negative, so I don't need absolute values this time. It wouldn't hurt to write them, you can still write them, but not necessary. And then times the fourth root of 5m squared. So 3 times m squared times the fourth root of 5m squared. Alright, 19 part C. Alright, so we have a fifth root, so I don't have to worry about absolute values. This is an odd root. 160 is 32 times 5, so it'll be 2 to the 5th times 5, and then times n to the 8th. And product property, right, breaking this up to the fifth root of fifth powers times the fifth root of not fifth powers. 2 to the 5th is clearly a fifth power. 5 to the first is not. And n to the 8th can be broken up to n to the 5th times n to the 3rd. And the fifth root of 2 to the 5th is 2. Fifth root of n to the 5th is n. No need for absolute values. It's an odd root. Times the fifth root of 5n cubed. And there you go. Wonderful. And I'm continuing to do this for a while. All right. So number 20. Part A, square root. So again, factoring the radicand completely. This would be 25 times 7. So 5 squared times 7. And then times, n to the 13th. Rewriting this with the product property, the square root of some squares times the square root of 9 squares. 5 squared is clearly a square. 7 to the first is not. And n to the 13th can be broken up to n to the 12th times n to the first. Square root of 5 squared is 5, no need for absolute values. Square root of n to the 12th would be n to the 6th. Also no need for absolute value there, because n to the 6th, that'll never be negative for any real number of n. Times the square root of 7n. And there you go. Okay, now we have a fifth root. So I'm looking for fifth powers, right? First I'm going to break up the radicand. Now 512, that's 2 to the 9th. It's 2 to the 9th power. And then you have times p to the 5th. Then break it up to a fifth root of fifth powers times a fifth root of not fifth powers. 2 to the ninth can be broken up as 2 to the fifth, right, a fifth power, times 2 to the fourth, which is not a fifth power, a power less than 5. And then p to the fifth is clearly a fifth power, so we have times p to the fifth under here. So fifth root of 2 to the fifth would be 2, fifth root of p to the fifth would be p, and then we have times the fifth root of, now 2 to the fourth is 16. Right, so you should be able to write your numbers. If it's just numbers, you should be able to simplify that. So yeah, 2 times p times the fifth root of 16. Okay. Part C, another fourth root, another even root. Let's see. This is the fourth root of, now 324, that'd be 4 times 81, so 2 squared times 3 to the fourth. That's 4 times and then 81, right? 2 squared times 3 to the fourth. Yeah. And then times q to the seventh, right? And then once again, break it up with the product property. Fourth root of fourth powers times a fourth root of non-fourth powers. Now 2 squared doesn't have a fourth power in it, so that's just going in the non-fourth power radical. 3 to the fourth is clearly a fourth power, so I'll put that in the fourth power radical. Q to the seventh can be broken up as q to the fourth power, times q cubed, with a power less than 4, not fourth power. The fourth root of 3 to the fourth is 3, no need for absolute values around that. The fourth root of q to the fourth would be, q, but that needs to be made non-negative, right? Absolute values are necessary around the q to the first. Then times the fourth root of, 2 squared is 4, q cubed, 4q cubed. Great. Alright, I'm still doing this, but now I think in the next examples we have some expressions with a number in 2 variables. Oh my goodness. But it's still, the radicand is still a product. Alright, the radicand is still one big product that I need to break apart, alright, with the product property. Okay, so we have the square root. Now, 147 is 3 times 49. So that's 3 times 7 squared. I think we saw that earlier in the video as well. 3 times 7 squared, and then you have times m to the 7th times n to the 11th, all one big product. And once again, I split it up with the product property to the square root of squares times the square root of non-squares. Now 3 to the first, that's a non-square. 7 squared is definitely a square. M to the 7th could be broken up to m to the 6th times m to the first, square and non-square, and n to the 11th could be broken up to n to the 10th, a square, times n to the first. Alright. So now we have, the square root of 7 squared is 7. The square root of m to the 6th would be m cubed, and n to the 10th, the square root would be n to the 5th. And m cubed, n to the 5th, those are both odd powers, so they need absolute values. And then you could put absolute values around each individual one, that'd be totally fine, or the whole thing. Just the whole variable product there. But I would need absolute values around these, right? This m cubed and n to the 5th, to ensure that we get the non-negative square root that the symbol asks for. And then times the square root of the rest, right? The square root of 3 times m times n, like that. Wonderful. And again, if you want to test it out, replace m and n with some numbers that you choose and use a calculator, see if the original value is the same as this value here. And, they should be. Okay. Part B, got a cube root. 48 is 16 times 3. That's 2 to the 4th times 3. And then you have x to the 6th, y to the 7th. And product rule, breaking it up to the cube root of cubes times a cube root of not cubes, right? Things with powers less than 3. Now 2 to the 4th you can break up to 2 to the 3rd, right? A cube, times 2 to the 1st, right? Thing with a power less than 3. 3 is definitely not a cube, right? So I have times 3 in this radical with no cubes. X to the 6th is a cube, right? That's a power that's a multiple of 3. That'd be x squared cubed. And then y to the 7th you can break up as y to the 6th, a cube, times y to the 1st. And the cube root of 2 cubed is 2. The cube root of x to the 6th would be x squared. The cube root of y to the 6th would be y squared. And because it's an odd root, I don't have to worry about absolute values at all, no matter what the powers are. And then times the cube root of the non-cubes, right? 2 times 3, though, is 6, and then you have y, right? The cube root of 6y. And you have 2 times x squared times y squared out in front. Great. Alright, see, I'm doing a 4th root. So once again, first thing I'm doing is factoring the radicand completely. 32 is 2 to the 5th. And then you have x to the 5th, y to the 4th. Then a product property. 4th root of 4th powers times a 4th root of non-4th powers, right? Things with powers less than 4. 2 to the 5th can be broken up into 2 to the 4th, right? A 4th power times 2 to the 1st. X to the 5th, same way. X to the 4th times x to the 1st. And y to the 4th is a 4th power, just y to the 4th there in the 4th power radical. Alright, so this is 2xy, but remember, it's even root, need absolute values around these, because x times y, this can be a negative thing. So I'm going to put absolute. Now you can put absolute values around x and y individually if you wish, but the product of absolute values is the absolute value of the product. You probably have seen that property. I put that property up in the last video on section 8.1 stuff. So you can have the absolute value around x, y like that, and then times the 4th root of 2x. 2 times the absolute value of x, y times the 4th root of 2x. Fantastic. Okay. Alright, here we go. Keeping on. We've seen 96 before, right? 22 part A, doing a square root. Again, I'm breaking up the radicand, factoring it completely. 96 is 32 times 3. That's 2 to the 5th times 3. And then you have times r cubed times s cubed. And I want to break it up to the square root of squares times the square root of non-squares. Now 2 to the 5th you can break up to 2 to the 4th, a square. Right? That's 2 squared squared times 2. And then 3 is, going to go in the non-square radical times 3. R cubed can be broken up to r squared times r. S cubed the same way, broken up to s squared times s. Now the square root of 2 to the 4th is 2 squared, which is 4. Right? And the square root of r squared is r, square root of s squared is s, but I need absolute values around that. Remember, it's an even root. So this r times s, yeah, that can be negative for your choice. If you choose r to be negative, s to be positive, that'd be a negative number. I don't want that, right? So because it can be negative, I need to ensure that it's not negative by throwing absolute value symbols around it. All right. This is only for even roots. And then times the square root of 2 times 3 is 6, and then times r times s, right? 6rs inside the radical there. Okay. Alright, next is a cube root. So again, first thing I'm doing is factoring the radicand. Now 80 is 16 times 5, that's 2 to the 4th times 5. And then times, x to the 7th, y to the 6th. Break this up into the cube root of cubes times the cube root of not cubes. 2 to the 4th I can break up to as 2 to the 3rd times 2. And then 5 will go in with the times 2. X to the 7th is x to the 6th, right? That's a third power, a multiple of 3, times x, right? Which is not a third power. And then y to the 6th is a third power. It's y squared cubed, right? Y to the 6th will go in that first radical. Alright, then taking the cube root of 2 cubed is 2, x to the 6th would be x squared, y to the 6th would also be y squared, and then you have this, times this cube root over here times the cube root of 10x. Right. Okay, we saw 80 already, so I know how to factor it. We got a fourth root though this time, right? With fourth root of 2 to the 4th times 5 times, and then x to the 8th, y to the 9th. Once again, product property. I want fourth root of fourth powers times a fourth root of not fourth powers, things with powers less than 4. 2 to the 4th is a fourth power, 5 is not. X to the 8th is a fourth power, right? It's a multiple of 4. Y to the 9th isn't, but you can break it up to y to the 8th, which is a fourth power, times y. Alright, and then fourth root of 2 to the 4th would be 2. X to the 8th would be x squared, right? Because that's x squared to the 4th. This is also y squared to the 4th, so times y squared. Now, this here, x squared, y squared, for real numbers x and y, this is never negative. So I don't need absolute value symbols this time, right? Because of the even powers. And then when we have times the fourth root of 5y. So 2x squared times the fourth root of 5y. Great. Alright, let's keep doing it. Same stuff. I got like 2 more questions with 6 more parts that are all like this. Okay, first part there, 23 part A. First thing every time, I factor the radicand completely. Now 192, let's see. 192 be 2 times, not 100, 2 times 98, no. 2 times 96, right? 180 plus 12, yeah, 182. Oh boy, and this is 4 times 24, right? That'd be 80 and 16, 180 and 12, yeah. And this is 4 times 6, and this is 2 times 3, 2, 2, 2, 2. So yeah, lots of 2's. So that's 2 to the 1st, 2nd, 3rd, 4th, 5th, 6th. 2 to the 6th, 64 times 3. Yeah, that's 182. So 2 to the 6th. Sorry about the delay on that. I've been talking for too long here. 2 to the 6th times 3. That's 192. And then you have q to the 3rd, r to the 7th. So once again, I want to use the product property, break it up to the square root of square root of squares times square root of non-squares. 2 to the 6th is a square, right? That's 2 cubed squared. 3 is not a square, so times 3 there. Q cubed, I can break up to q squared times q to the 1st. R to the 7th is r to the 6th times r. Right? And then the square root of 2 to the 6th would be 2 cubed, that'd be 8. Alright, 2 to the 6th is 64 as well, right? That'd be 8 square root of 64. Then q squared is q, square root of r to the 6th would be r cubed. Now do I need absolute values around this? Absolutely. These are both the odd powers, so they can both end up giving me a negative result. So I'll throw absolute value symbols around that qr cubed. Alright. And then we have times the square root of 3QR. There you go. Alright, great. Cube root of 54, m to the 9th, n to the 10th. Once again, breaking up the radicand. 54 is 2 times 27, and 27 is 3 cubed, so this is 2 times 3 cubed. Then we have m to the 9th, n to the 10th. And now I want the product property to be used, right? Break it up to a cube root of cubes times a cube root of non-cubes. 2 is not a cube. 3 cubed is, clearly. M to the 9th is a cube, right? That's m to the third. And n to the 10th can be broken up to n to the 9th, a cube, times n to the 1st. Cube root of 3 cubed would be 3. Cube root of m to the 9th would be m cubed. Cube root of n to the 9th would also be n cubed. And it's an odd root, so I don't need to put absolute values. There's no need. Times the cube root of 2n. Wonderful. Alright, fourth root time. 23 part C. This is a fourth root. Now 81 is just 3 to the 4th. So that's fourth root of 3 to the 4th times a to the 9th times b to the 8th. And I break it up, product property, right, to a fourth root of 4th powers times a fourth root of non-4th powers. 3 to the 4th clearly is a to the 9th can be broken up to a to the 8th, right? A 4th power. Power is a multiple of 4 times a to the 1st. And b to the 8th is a 4th power, so b to the 8th. 4th root of 3 to the 4th is 3. A to the 8th would be a squared. B to the 8th would be b squared. And I don't need absolute value symbols around these. Right? Yes, it's an even root, but these are both even powers. Anything to an even power is going to be not negative. So no need for absolute values, and then times the fourth root of a. Great. Now I got one more page with examples like this, and then we get into some different kinds of examples. Examples with negative radicands. Right? We haven't seen any negative numbers inside our radical symbols yet. They're coming up. All right. So example 24, part A. So once again, square root. Now this is 2 times 75, which is 3 times 25. This is 2 times 3 times 5 squared, right? 6 times 25, 150. Perfect. All right. Times m to the 9th times n to the 3rd. And then I break it up with the product property. The square root of squares times the square root of non-squares. 2 is not a square times, 3 is not a square. 5 is being squared there, 5 squared. M to the 9th I'd have to break up to m to the 8th, which is a square, something with an even power, times m to the 1st. And n to the 3rd I'd have to break up to n squared times n. Alright, now the square root of 5 squared is 5. Square root of m to the 8th would be m to the 4th, which will always be not negative. Alright, it's an even power. Square root of n squared, though, is n. That just the n needs the absolute value around it. Right, because that can be negative, and I'm taking an even root. I don't want, this symbol means I want the non-negative root. Right, so I need to ensure that with an absolute value symbol around my result. Then times the square root of 6mn. 2 times 3 is 6 times m times n. And there you go. All right, next we have a cube root. Now 81 is 3 to the 4th. Then we have p to the 7th, q to the 8th. I want to break this up with the product property. Right. Cube root of cubes times cube root of non-cubes. 3 to the 4th can be broken up to 3 to the 3rd times 3. P to the 7th broken up to p to the 6th, right? Perfect cube, that's p squared cubed times p. Q to the 8th would be q to the 6th times q squared. Right, so perfect cubes and non-cubes with powers less than 3. Cube root of 3 cubed would be 3. Cube root of p to the 6th would be p squared. The cube root of q to the 6th would be q squared. Right. So 3p squared q squared times the cube root of 3pq squared. Great. Alright, then the last example like these, and a fourth root, so I'm looking for fourth powers, right? So first thing I do is break it up again, right? Break up the radicand. Now 162, that's 2 times 81. So 2 times 3 to the 4th. Right? We saw 81 is 3 to the 4th a bunch so far this video. Times c to the 11th times d to the 12th. And once again, I'm using the product property to break this up to the fourth root of fourth powers times the fourth root of not fourth powers. 2 is not a fourth power. 3 to the 4th is. C to the 11th would have to be broken up to c to the 8th, right? That's a fourth power, multiple of 4, times c cubed, right? There's a power that's less than 4, right? Not a fourth power. And then d to the 12th is a fourth power. Right? That'd be d cubed to the 4th, right? Power to a power. Fourth root of 3 to the 4th is 3. Fourth root of c to the 8th would be c squared. No need for absolute values around that. That's always going to be non-negative. But the fourth root of d to the 12th is d cubed, and that needs absolute value symbols around it, right? Because d cubed can be negative if you replace d with a negative number. So I have 3 times c squared times the absolute value of d cubed, then times the fourth root of 2c cubed. Okay, wonderful. Alright, so now getting into some examples of radicals with a negative radicand. Now, I hope you remember here that when you take an odd root of a negative number, the result will be negative. It'll just be the opposite of the odd root of that positive number. So with odd roots, right, the odd root of a negative number is, you can just pull the negative out if you want, and you'll get the same result. Okay. So let's see, 864. Let's factor that. 864. Now that's clearly a multiple of 4. In fact, I think it's a multiple of 16. But let's see, 4, that'd be 2. And then 216. Yeah, and 216 is 6 to the 3rd power. So I have 2 cubed, 3 cubed, and there's 2 times 2 from the 4 earlier. So this is 2 to the 5th times 3 cubed. Right? So this is negative. Just make sure you have the negative sign. This is going to be negative at the end. And then I have the cube root of, 864 is 2 to the 5th times 3 cubed. Breaking this up, this would be negative, and then negative, and then break up the cube root to the cube root of cubes times the cube root of non-cubes. 2 to the 5th can be broken up to 2 cubed times 2 squared, and 3 to the 3rd is a cube. So yeah, so this is just negative 2 times 3 times the cube root of 4. So this is negative, 2 times 3 is 6. Negative 6 times the cube root of 4. And then once again, because it's been a little while, let me pull up the calculator. Let's just test this one real fast. Alright, so it's been a while. Let's do the cube root of negative 864. All right, getting this number here, a negative number, right? And now let's take, negative 6 times the cube root of 4. And you're seeing it's exactly the same thing. Right, and that should be happening if you're doing all these correctly. All right. Now, the next example, real easy. This is an even root. But, we have a negative radicand. And remember, when you're taking the even root, square root, fourth root, sixth root, etc., of a negative number, this is simply, for the moment, we're just going to simply say that this is not a real number. In later sections, later videos, we'll talk about imaginary numbers and how to express even roots of negatives as these imaginary numbers. But for right now, we're just going to simply say the even root of a negative number is not a real number. Very simple. Okay, 26. Part A is just like part A from 25. Again, odd root of a negative, you can pull the negative out. I'm just going to say this is the opposite of the fifth root of positive 486. I just know it's going to be negative at the end. All right. This is negative. Now the fifth root of, now 486, let me do some factoring again here. This would be 2 times 243. This is a multiple of 9. 9 times 27. Oh, geez, okay, so this is 3 to the 5th. Yeah, this is 3 to the 5th. So 2 times 3 to the 5th is 486. All right. Okay, and then, yeah, that's it. All right, 2 times 3 to the 5th is 486. And then I'm breaking this up. We have negative out front all the time. And I'm breaking it up to the product of fifth root of fifth powers times the fifth root of not fifth powers. Now the only fifth power I can pull out of here is 3 to the 5th, clearly, and the only factor left over would be 2. And the fifth root of 3 to the 5th would be 3. So I have negative, 3 times the fifth root of 2. And there you go. And again, use your calculator, see if the fifth root of negative 486 is the same as negative 3 times the fifth root of 2. And then just like example B of number 25, look at example B of number 26 here. We have an even root of a negative number. So again, this is not just simply saying for right now, this is not a real number. All right, there's no real number you could raise to the 6th power to get negative 64. Okay. All right. Okay, 27 part A, real easy one. Real easy one. It's an odd root of a negative, so it's going to be negative, the opposite of the fifth root of the positive, right? The opposite of the fifth root of 32. And we've seen 32 earlier, right? This is the fifth root of, 32 is 2 to the 5th. So this is simply negative 2. Right? Negative 2 to the 5th power is negative 32. So the fifth root of negative 32 is negative 2. Excellent. Easy one there. Once again, for part B, I have an even root of a negative number. Oh man, right? Now, this is not real. There is no real number you could raise to the 8th power to get negative 1. Right, so this would be another imaginary. Right? We'll talk about that later, right? Later videos. But that's it, not a real number, the end. Number 28, part A, cube root of negative 8, oh, this is negative 2. Also, right, negative 2 to the third power is negative 8. This one was real simple. And then part B, another even root of a negative radicand. So once again, this fourth root of negative 16 is not real. Not a real number. Very easy. Right. Cool. All right. Now, these last examples have some parts of the problem, some parts of the question that are in a radical, and some that are not. So look at number 29, part A. So you have one term that's not in a radical, 5, plus, and then one term that is in a radical, square root of 12. The term that's, anything that's not in a radical, you don't do anything really with till the very end. But we're only asked to simplify the radical. Alright, so I'm going to kind of do these quickly. We have 5 plus, and then the square root of 12 would be the square root of 4 times the square root of 3. Now the square root of 4 is 2. So we have 2 times the square root of 3. Right, now again, I leave it to you to simplify. I've done so many examples in this. Go back and look at how I did this, with other square roots early on in the video. You should be able to do this after a bunch of practice by this point. And these don't go together. These do not go together. All right. Here's a mistake. I'm going to circle this. This is as it gets. Because one is a radical term, the other one is not. You can't put radicals together. You can't add or subtract radicals with non-radicals. Here's a mistake. And I'll show you with the calculator that it is indeed a mistake. Very often I'll see people do this and say, oh, this is equal, take 5 plus 2 and say, oh, that's 7, and then you have times the square root of 3 like that. Well, let me show you why that's wrong. Let me show you why that's wrong. Pull the calculator up. Let's look at our original expression. It was 5 plus the square root of 12. And you see I'm getting here 8.464 or whatever. Now let me put in this mistake value, 7 times the square root of 3. And you see it's not the same number, right? This is bad. I'm going to cross it out with an actual color that works. That's bad. That is not the same value as the expression I was given. And that's because you can't add radical terms with non-radical terms. So that's as simple as I can get that. And let me show you. Let me show you that that's actually the true value. Let me take 5 plus then 2 times the square root of 3. Also 2, oops, wrong thing. All right, 5 plus 2 times the square root of 3. Also remember, see, it's 8.464, the value of the original expression that I wanted. Also remember your order of operations. Remember, multiplication is done first, then addition. So you would take 2 times the square root of 3 first, and then add the 5. All right. But once again, I'll say it, radical terms and non-radical terms don't go together. All right, you would leave them like that. And we'll see a video later. We'll see in a later section of this text adding and subtracting radicals. And that concept will be brought up one more time. All right, so let's continue on here with more radical simplification. So again, here in part B, I have I have a fraction. Numerator got 10 minus the square root of 24. Now all I'm going to do in the beginning is simplify that square root of 24. The 10, the 2 in the denominator, not touching those yet. So we have 10 minus, and then denominator of 2. Now the square root of 24, that'd be the square root of 4 times the square root of 6. That's 2 times the square root of 6. And that's as simple as that radical gets. Now this is great and everything. The radical is simplified, but now let's simplify the fraction. Also, right, you should be simplifying everything you see. Now I hope you remember how to simplify a fraction. You factor the numerator, factor the denominator, and cancel any common factors. Look at the terms of the numerator. This is 2 times 5, right, 10. And this is 2 times the square root of 6. So I could factor a 2 out of the numerator, and I'd be left with 5 minus the square root of 6. Right, and you can redistribute and check. 2 times 5 is 10, minus, and then 2 times the square root of 6. Got it. Divided by, and the denominator is 2. And you see the common factor in the numerator and denominator, right? They both have a common factor of 2. Those become 1, and I'm left with just 5 minus the square root of 6 at the very end. And that's, as simplified as the result gets. All right, once again, let me just double check that. All right, pull up my calculator. Now the original expression, the numerator has 2 terms, so I'm going to put that in parentheses. So in parentheses, I've got the numerator 10 minus, and then the square root of 24. And then get out of there and close the parentheses. There's the numerator divided by 2. All right, we're getting a value of 2.55051, right? Now let me punch in the expression I got at the end after simplifying the radical and then simplifying the fraction. 5 minus the square root of 6. 5 minus the square root of 6. And it is indeed the same number. Fantastic. Right, and it should be that way, right? Especially when you're dealing with these solely numerical expressions without variables. If there are variables, just plug in numbers for the variables and see if it works. All right, 30 part A. Again, the 8 here I'm not touching. That's not a radical. No square root symbol, no radical symbol. The square root of 96 is the square root of 16 times 6. Square root of 16 is 4, and then you have times the square root of 6 still. Again, I leave it to you to figure out how I did this. I've done a bunch of simplification now in this whole video. You should be able to do this after practicing that much. And that's it. That is it. Don't, as I said in example 29 part A, don't put these together. You would not do the addition, right? Multiplication happens first, then addition. Don't put the 8 and the 4 together. This is not 12 times the square root of 6. All right, please, 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 please don't do that. Radical terms and non-radical terms don't get added together. They can't be combined. Added or subtracted. All right, and again, I'll leave it to you for, go to a calculator and check that. All right, here, this is very similar to part B of 29. First, I'm going to simplify the radical, the square root of 80. All right, 80 is 16 times 5, so that's 4 times the square root of 5. All right. Square root of 16 times the square root of 5. And then we're dividing by 4. Now, if you can do the thing where you factor out a 4 up top, right? See, there's a common factor of 4. And then if you pull out a factor of 4, you'd have 2 minus the square root of 5 left over. And then 4 in the denominator, and the 4's cancel, and I'm left with 2 minus the square root of 5. Or you could take each term of the numerator and just divide it by 4, right? 8 divided by 4 is 2. And then when you divide these two, the 4's will cancel, you'll be left with the square root of 5. So you get 2 minus the square root of 5 either way. And once again, test it out, punch them in the calculator, see that they're the same value. All right. And here is the final page. All right, and these are pretty similar to what we just saw. Just simplifying the radicals. 1 plus the square root of 45 is the square root of 9 times the square root of 5, so 3 root 5. 1 plus 3 times the square root of 5. And again, don't add these. One's a radical, one's not. They don't go together. Here, got 3 plus, square root of 90. 90 is 9 times 10. Square root of 9 is 3. So it's 3 times the square root of 10, using the product rule. And then divided by 3. And then when I divide each of these terms by 3, 3 divided by 3 is 1 plus, and then when I divide the second term by 3, the 3's cancel, you got square root of 10. Or you could have factored 3 out and canceled the 3's. Either way, it's 1 plus the square root of 10 when you're done. And final question, 32 part A, and 3 leave alone. Square root of 125. Now this is 25 times 5. Square root of 25 is 5. So this is 5 times the square root of 5. Alright, square root of 125 times the square root of 5 would be, square root of 25 times the square root of 5 would be the square root of 125. And this is it. And please don't add these. Don't make this 8 times the square root of 5. This is a non-radical. This is a radical. Radicals and non-radicals do not get added together. And then finally, numerator, we have 15 plus the square root of 75 is the square root of 25 times the square root of 3. So 5 root 3. And then we're dividing each of these terms in the numerator by 5. Now you could factor a 5 out and cancel it, or just divide each term by 5. 15 divided by 5 is 3, plus, and then 5 root 3 divided by 5. The 5's would cancel, you'd be left with the square root of 3. And there you go. You're left with 3 plus the square root of 3 at the end. And again, don't add these together. These don't go together. One's a radical, one's not. They don't get added. And once again, I leave it to you to check these on your calculators. Right? Punch in the original expression, punch in the final expression. They should be the same. Alright. So I hope that watching me go through all the parts of all 32 of these questions helps you when you're simplifying radicals on your own. And thank you very much for watching.